Welcome back. In Lesson 12, we're going to talk about tangent planes and their use in multivariable differential calculus. Let's talk about the general approach that we take to developing calculus tools in this class by reminding ourselves of the structure of the lessons so far. In the early videos like Lesson 1, 2, and 3, we looked at this structure very often. In the beginning of our work, we started with the study of arithmetic, aka vectors and vector operations like vector addition and scalar multiplication. So this was something like Lessons 1 and 2. We then moved on to the study of algebra, meaning to say the study of algebraic properties of vector operations, and we focused most heavily on the new operations that you hadn't really seen before, including the two norm, the dot product, and the cross product. So this was like Lessons 3 and 4. We then moved on to our study of pre-calculus, tools that are necessary to understand and interpret calculus graphically. These included the graph of multivariable functions, the graph of vector-valued functions, as well as domains, ranges, surfaces, blah, 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 blah. So you could call this thing like Lessons 5, Lesson 6, and Lesson 7. Once we had these tools in our pockets, we moved on to the development of calculus, which in this class you could really say the development of partial derivatives. This corresponded to Lesson 7 all the way through Lesson 14, which we haven't finished yet. Of course this is Lesson 8. We've gotten to the point where we've developed the gradient operator, which is the vector of partial derivatives, and we're starting to be able to analyze multivariable real-valued functions using this gradient operator. Tangent planes allow us to conduct this analysis, and we'll talk about what we mean by that. The whole idea of Lessons 8 through 11 really was focused on developing the technical tools that we need to take derivatives of multivariable functions. We also talked about the explanation of the derivative and the significance of these derivatives graphically. That was the 5-step program for salvation that we returned to over and over and over again. Now that we have that under our belt, in Lessons 12, 13, and 14, we're going to move on to studying techniques to apply the multivariable derivative, the gradient of some multivariable function, and we're going to analyze the behavior of the function using this gradient. Notice this is a vector-valued output. This is kind of a more advanced method of saying that f is indeed multivariable by just putting vectors on the inside. When we look at developing methods to analyze a function, we're going to focus heavily on the idea of optimization, which we saw in Math 1A. To start the concept of optimization, we're going to look at generalizing the idea of a tangent line to a single variable function. Before we jump into the concept of a tangent plane, let's go ahead and recall the second derivative test from Math 1A. Recall that the second derivative test was designed to help us find maximum and minimum values on the graph of a single variable function. And we can do better than that. Boom! We can actually state the theorem called I would call it the second ordinary derivative test because it's done for ordinary functions. So suppose that we have a single variable function with a real valued output. And then suppose that the second derivative of this function is continuous around some input point c. Finally, suppose that f prime of c is 0. So the derivative of the function at the input c is 0. The second derivative test for single variable functions had 3 conditions, or 3 different things that we could check. If the second derivative of the function at the point c was positive, we said that the graph was concave up, and thus the point with the horizontal tangent line and concave up behavior was a local minimum at the input x equals c. The second case was if the tangent line was horizontal at a particular point and the graph of the curve was concave down at that point, aka the second derivative was negative, then the graph of the function had a local maximum at x equals c. And then finally, in the second derivative test, if the second derivative of the function was 0 and the first derivative was 0, so horizontal tangent line and the curvature cannot be ascertained from the second derivative, we said that the second derivative test was inconclusive. As a friendly reminder to really bring the point home, this test started with finding input values f prime of c equal to 0. These values, these input c, this is where the slope of the tangent line was 0. We also called these one of two different critical points. In order to run the second derivative test, we needed to find the location of the horizontal tangent lines. Let's switch over to Mathematica and get an idea of what this looks like and an idea of how we might generalize this into multivariable functions. Bam! Here we are in Mathematica. This is a visualization. The blue curve here is a graph and the red line is a tangent plane. I'm not going to show you how to code this up necessarily, just because the idea that I want is to generalize what we're looking for in the second derivative test. Later in these videos, I will show you how to create tangent planes. For now, all I want to say is, in the second derivative test, we needed to start with a function, that's the blue curve, y equals f of x. And then we also needed to find points where f prime of x was 0. In other words, we wanted to move the tangent line. This is used manipulate function. So here we go. So that it was horizontal. The slope of the tangent line is horizontal, right? Right there. So we would want to find that point. So find the derivative, set it equal to 0, and then solve. Right? And then we go down this way, etc., etc. At that point right there, the one we're visualizing on the screen, we see that the derivative f prime at c, if that point is c, that derivative is 0, and the graph of the function is concave down. Using the second derivative test for ordinary functions, for single variable functions, we would say that that point represents a local maximum. One of the things that we're going to do is generalize this second derivative test from ordinary functions to partial functions. That's the grand conclusion of lesson 13. Let's visualize how we might do that. Here we are with the graph of a multivariable function, kind of a similar behavior, elliptical paraboloid. And then instead of a tangent line, notice that we have a tangent plane, which we can kind of move around. Woo! It's kind of fun, right? Yay! This tangent plane, there's a red thing that we're doing right there. That's what we're going to construct in lesson 12, the lesson we're currently in, how to find the equation for that. But more importantly, in lesson 13, what we're going to see is if we want to maximize or minimize, we're looking for points right at the top. Oh, sorry. Let's see if I can get it with my hand. Yeah, there we go. It looks like just about that, right? That's the normal vector there is going to be in the direction 0, 0, 1. Okay, and then we could say that, okay, as long as the tangent plane, I didn't get it at all. As long as the tangent plane is in the direction 0, 0, 1, we would say that that represents a slope of 0, and then we're going to look at somehow curvature, so second partial derivatives, to figure out whether the thing is concave down, concave up, etc. So to do this, we're going to develop the second partial derivative test in lesson 13. But before we do that, we need to figure out how to find tangent planes, and then more importantly, how to find when they are horizontal. That is lesson 12. Follow me to the next video where we develop a tool that will help us develop the equation for a tangent plane to a surface. See you there.